All right, team. We're really excited to share Voltaic cells with you and electrolytic cells. Team, we're talking about batteries right now. And the chemistry of batteries, to me, is perhaps one of the most important parts of our day-to-day lives. Let's pretend that you could not use batteries. You wouldn't be able to use a phone, you wouldn't be able to use a laptop, you wouldn't be able to use a vehicle. The Voltaic battery, these galvanic or Voltaic cells, these electric batteries, is the chemistry behind almost everything that we do in our lives day to day now. Now, it didn't used to be as humans, but right now it is. And I'm going to introduce a very simple version of what that looks like. Okay. Now, we need to remember a little bit about oxidation numbers. And it's really good this time of year to be able to review, okay, how do we get all of these oxidation numbers? Now notice these free elements are all 0, 0, 0, 0, 0, 0, okay? But then we've got a chlorine that's -1, just like its charge. And so the sodium has to balance it out. And then we've got a -2 times 4 becomes a +8. Now these other guys have to balance them out. And that's how we find the oxidation numbers for different compounds. And this is a good thing for you guys to review, and I'm expecting that you review it before the exam. A shortcut is you can look at a reaction and be like, okay, the loss of electrons is an oxidation. Leo the lion says Gur. The gain of electrons is a reduction. So we've got a copper 2+, which it is lacking 2 electrons, and it gains 2 to be able to be balanced and have no more charge. Therefore, this is a reduction. Magnesium is whole. It has no charge. It's in a good state. It loses 2 electrons to become 2 positive. It lost them so that it has become oxidized. And we can see that in this battery right now. Zinc is falling apart in this battery. Literally, we have one type of metal that's falling apart. As it falls apart, it's releasing these zinc anions, okay? And as it's falling apart, each time it releases a zinc anion, it sends 2 electrons through this wire to the copper, which it's sitting in a copper solution, this copper sulfate solution. And so these copper ions that are floating around in the solution now come on and join. Every time that we have 2 electrons land here, this copper bar is growing, okay? And so what we have is we have this left side that's losing electrons. Leo the lion says Gur. This is a loss of electrons. This is oxidation. And we now know that anox is the anode, okay? And then over here we have a reduction, RED, a red cat is the cathode. A cathode is the positive side of the battery. The anode is the negative side of the battery. And one way that you can think about it is the electrons are coming from the negative side of the battery. And that's one way that you could think about that. So let's keep going. So we're looking at this cell. And one of the things that we did in class is we looked at this and we said, okay, let's break these down by half reactions. These are called half reactions. And you can go zinc loses 2 electrons. It's now in this form in the products. In the reactants, we've got copper, the anion floating around. It picks up 2 electrons from the wire. It's now a more copper, it's a solid copper, and we can cancel out the electrons, and we're left with this left over. Again, the one that's oxidized, which in this case, loss of electrons, Leo, oxidized, zinc is the anode, anox. And then the cathode is the red cat, the reduction side. The copper is the reduction side. And we can see what that looks like. There's the annotation that they use sometimes to be able to show that this is a battery. You don't see that too often, but I thought I'd put it here so you guys could see it. This battery is thermodynamically favored. Therefore, delta G is going to be negative. It wants to happen as soon as we set it in here. Okay, but it's important. Why do we have the salt bridge? Why is this KCl here? Because as we lose, okay, we're going to get zinc 2+, zinc 2+, zinc 2+. There's going to be a positive charge building up on this side of the battery. We have a salt bridge so that the negative anions, these Cl's, can fly over and help balance out this so that it will stay thermodynamically favored. And then on this side, as we lose all of our copper, and this copper continues to grow as the battery is running, now we have a buildup of a negative charge. All we're left with is all these SO4s floating around here. So the potassium flies down here and then neutralizes it. We're good. We're done. We got this. Okay? And so that's what, if we pull out that salt bridge, this is going to very quickly go to equilibrium. Delta G is 0. There's no more energy. We have to have that salt bridge to be able to continue putting charges on either side. The charges have to go back and forth, to be able to keep the battery so that it continues to move forward. So here's, I don't even know what's happening here. Let's get out of here. Okay, the salt bridge, I already talked about the salt bridge. Let's talk about electrolytic cells. Electrolytic cells are not thermodynamically favored. They need electricity to have the reaction move forward. So you can see we have the notation for a battery right up here at the top. And that's one way that we can tell that it's electrolytic. It needs electricity or a battery or an energy source to be able to make it run. And this is, like I said, what we call an electrolytic cell. What we have here, and we have the Cl on this side. This is the, on this side we have the anode. And then over here, what do we got? We got the Na turning to Na, which is the cathode. And that would be right there on that side. So there's the cathode. I don't love that this is reversed though. So yeah. That which is reduced would be, yeah. So in my opinion, we've got Na. Yeah, this would be the positive side, which would be the cathode. Okay, and this would be the negative side, which would be the anode. Yep, love it. All right, let's keep going. Let's rock and roll. Na is reduced, that's the cathode. Cl is oxidized, that's the anode. Now, they might ask you a question about electroplating. Based on this information, I put the energy source here. Okay, and so what we've got is we've got the electrons being released from our copper. And as the electrons are released, okay, they are flowing up and they're coming down and they're making this gain more of those electrons, and so therefore it's now picking up whatever metal is in the water here. And the metal that's in the water is the copper. As it's falling apart from here, it's leaving this copper and it's going and covering up whatever this metal is here. We call this electroplating, and this is one way that you can put a what's the word I'm looking for, like a gold plating, some type of metal plating, a platinum plating around a coin, something else, so that you don't have to make it solid gold. You can make it, just have a layer of gold on the outside, which is sad, but this is the chemistry behind it, team. We've all been a little let down in the past where we're like, what? It's just gold plated, it's not solid gold. But this is how we do it. And we have this one metal falls apart, and as that metal goes into the liquid, it then is picked up by the silver, by this other piece, and then it's covered in copper. Team, have a great day. I wish you success. Good luck.